This little Lego brushless motor is fast. Like really fast. But just how fast can we get it to go if we max it out? In my previous video, I used some Lego to make a bunch of brushless motors, from practically tiny to needlessly large. And I also caught some flack for not pushing them as fast as they could go. So today, we fix that. We're gonna push these things hard. I want to know just how fast they are, how much torque they produce, how much power they draw, and how they compare to a standard Lego XL motor.
Wow.
Now I've also created a couple of torque monsters that can not only spin fast, but can also do some serious work. Are any of these actually practical, or are they just a bit too extreme? Well, let's find out. Now to start with, we're gonna need some better motors than my first batch. I want to make a record-breaking absolute speed monster, so using a smaller number of bigger magnets will help. My goal here is something that's compact but crazy fast. Now to keep it as compact as possible, we're going to create a tiny 6-core stator. And I want to pass a reasonable current through them, so the wire for the coils is reasonably thick at 24 gauge. Now we have 3 phases made of 3 tight pairs of coils, and from here we can build the rest of the frame. I really want this to be as small as possible so that it can be useful in future Lego builds. And I'll allow for a gear reduction as well to get more torque out of it for future builds. Though for today, we'll largely test the power and speed straight out of the rotor without gearing. I've also designed it to be modular, so it's easy to put in different magnetic rotors or gearing stages. Well, it's super basic, but I think it'll do its job pretty well. So let's chuck a wheel on her and give her a spin. I've seen some videos of brushless motors causing tires to expand, separating them from the wheel rim. So I want to know if I can do that with this motor. This is very low speed on the speed controller, and it's already looking sketchy. With the front-on view here, we can see that as the speed increases, the wheel expands. And if we increase the speed just a little more... cool. The tire expands so much it separates completely from the wheel hub. Nice. And what about with a bigger wheel? This tire is stiffer, but it's also bigger, so the forces on the perimeter of the wheel might be greater. I'm still only at about 15% power here, but I can already see this big tire separating.
Whoa!
Now the reason I made this motor is because it combines the best parts of these 3 motors I made previously.
This one had 8 smaller magnets, and the coils were thin wire and the back of them was a bit too far away from the magnets. This one has 16 smaller magnets, so it spins even slower but with a bit more torque, and the coil thickness was fine, but the coils are very far apart. This one then used larger magnets, but it uses the same coil design as this one here, and really this one is just way too big for it to be practical. So instead I made this thing, which is the best of all worlds. It uses nice thick wire, and the coils are super tight to each other with no gaps between them. For the magnets then I'm using 4 of these massive 15mm magnets. They're big so the torque is good, and because there's only 4 of them it can spin up to crazy speeds. Also, this one is smaller than all of the other 3.
Okay, before we put it through its paces though, let's first see how a standard Lego XL motor performs. At 9 volts. My meter here will tell us just how much power it's drawing.
1 watt without load. Let's see what it draws when I try and stall it. It's about 1.3 amps. 10 watts, 11 watts, 12 watts, and then it stalls.
Now, this is actually very impressive for such a tiny motor. And how fast does it spin?
My tachometer will track each rotation of this white piece.
Well, this XL motor is strong due to all of the internal gearing, but it is spinning quite slowly at only around 220 RPM at 9 volts. So how about our small brushless dude? This time I'm going to contain the magnets by placing a little lid on the rotor.
Hopefully now the magnets will be safe inside there.
Now let's see just how fast we can get this thing. I love the sound of this thing as it spins up. That sounds a bit like a race car. It'll be interesting to have it run a Lego drag racer.
Nearly 30. 31. 32. Whoa! Oh, nearly 40,000. And it looked like it was drawing about 10 watts at its peak speed. Not bad. Especially considering I was only about halfway on the speedometer.
So, this was our first attempt, But I'm going to lube it up and try again later to max it out. I still first want to run some more experiments before I risk destroying it.
I'm going to turn this on all the way up, and I'm going to try and hold this to stall it, and we'll see just how much it draws. Okay, she's off. Ow! Ow! Okay, that friction is crazy. I think I need some gloves or something. Let's see if these are thick enough. It's maxing out at 3.2 amps, which means there were some brief moments where this motor was drawing about 38 watts. Even though this little guy is not the most efficient motor, because it doesn't have ferromagnetic cores in the coils here, it moves so fast that at 37,000 RPM, if we just use a gear reduction like this one with 15:1, we can still get an output with 2,500 RPM at an absolutely unstoppable torque.
So at these speeds, I wonder if we can make a little Lego electric ducted fan. And a mount onto which we can pop our fan, and add a little casing for the fan.
Alright, let's see how our poor man's ducted fan works.
Oh, I don't know how fast this thing is blowing, but it sure feels windy.
Not bad.
Let's see what it does with a ping pong ball. And what about something a little bigger? It takes a sec, but it creates a reasonably concentrated breeze. But at this point, I'm curious to see just how much thrust is being created. With this jobby, we can see on the scale approximately how much thrust is being created. As we push the yellow piece, we can see the thrust in grams on the scale. I'm hoping that with this setup we can mount our various motors and see which of them creates the most thrust using the same propeller.
Now I think that if the distance from here to here, and then from here to the axle, so long as they're the same, then the thrust should more or less equal to what's on the scale.
To test if the setup actually works, let's first try this ducted fan. Now I'm pretty sure my hopeless design here will perform quite poorly, but I'm interested to see just how it does. Yeah, it sure does sound like it's making a lot of fuss for very little thrust. Just goes to show how important propeller design is.
I'm curious to know if this cover does anything at all.
Yeah, honestly it looks like the casing does very little for the thrust created here. I imagine a simple 3 or 4 bladed prop design will fare much better.
I'm kinda scared to take it higher. Yeah, the downside of these speeds is we're getting a lot of wear and tear around the axle here.
Even this bushing got lightly toasted.
Ugh, Lego's really not made for these speeds. This axle is totally knackered. I'm kinda curious to know what happens if I use a massive prop like this. Oh! Yeah, well, you spin it the wrong direction and break your prop. Yeah, what about this little guy? Let's see what this does.
Well, immediately we can see this outperforming the crappy EDF prop I made, comfortably reaching 43 grams.
Well, that is a lot better than the EDF. Okay, we have 3 new blades, each one with varying pitch angles to see which is better. Okay, a couple of small upgrades. I'm going to use an aluminium axle here, and I considered using these bearings, but actually instead, I'm going to use some of this super lube. I don't know if this will help much, but I'm just hoping it'll stop the Lego getting chewed up. Whoa, that's a lot smoother.
We'll allow it to draw up to 3.2 amps, which is about the limit the coils can take for this motor. This lube definitely does its job.
Very nice. Okay, let's try a blade with a 10-degree pitch angle. Let's give this a try. Not sure what that was. Well, that's why we wear our safety glasses. And let's just hope the 10-degree pitch wasn't the best blade we have. I have a suspicion that what happened is when I increase the speed, these coils kick back on the rotor and it might have toppled it this way. By shunting the motor this way, there's more weight leaning over this way. I'm hoping this will keep it more stable. Okay, let's try now with a 22-degree pitch angle. Okay, let's give this a wee try. Oh, it's already a nice breeze.
Let's take her up.
Wow!
About 40 grams at 25 watts. Well, out of the blades I tried, this one definitely performs the best.
60 grams of thrust. Oh, nope. Let me test it with the LiPo in case there's something weird going on with the power being delivered.
In retrospect, there was nothing wrong.
Nice.
The power supply just maxed out at 3.2 amps, preventing the rotor from being driven harder. And the LiPo, being only 11 volts, also maxes out at around 57 grams of thrust.
All in all, this is not a bad little performer considering it's coreless.
But how about we build a motor with ferromagnetic cores for the coils? In theory, this should be more efficient and provide much more torque. Now, the issue here is these plastic bushings, which will experience massive friction when the magnets are attracted to the metal cores. These will almost certainly friction weld themselves, which is why I'm going to try these LEGO compatible bearings. These should create a buffer and allow the motor to spin at several thousand RPM while under serious magnetic pull, without wearing itself down. I'll give it a wee gear reduction as well, just for compatibility for future projects. Now, I don't expect this one to spin anywhere near as fast, but the torque should be pretty damn good. There's definitely more resistance as the magnets pull and tug on the metal cores. And we'll zhuzh her up a little by giving her a nice little base. Now let's see how this motor fares with the same 3.2 amp limit.
She's wobbling. There we go. Okay, let's give her a tiny bit of juice. I'm maxed out. It's drawing about 20 watts maxed out. 1.6 amps. And let's see, is it powerful?
Of course, with this gear reduction, it's crazy torquey.
Oh, yes. Ow.
Honestly, this is probably way more torque than we'd ever need for a LEGO build.
Ow. That was dumb. The edge of the rotor is a bit sharp. And how's the ball bearing holding up? Excellent. Well, the bearing's rated for 50 kilos and 20,000 RPM, so it's holding up absolutely fine.
Now, of course, we'll need to see what speed this is running at.
Okay, let's give her some juice. Alright, let's max her out. It's fully maxed out.
About 3,400 RPM maxed out. Much slower than the coreless motor, but the magnetic cores focus the magnetic field, increasing the torque per amp. This is great for torque. So how does this motor fare on the thrust test?
Okay, place your bets. I think this one is not going to be spinning particularly fast, but it should be more efficient. So let's see how she blows. "22 grams at 20 watts. Let's go up. 30 grams at 25 watts. Yep, I've maxed out the speed controller. 2 amps, 12 volts, 24 watts. And the breeze is even blowing the plants a little way behind it.
So this is an axial flux motor, and even though we're using a bearing, there's still loads of friction here against it. So what if we instead create a radial flux brushless motor where the coils are on the outside and the magnetic core can spin on the inside of it, with much reduced friction? We'll start with some smaller magnets, but we'll fit 10 of them into the rotor. Now we're starting small, but I'm going to create another rotor with bigger magnets to compare with. And once again, to contain the magnets in case anything tries to escape, we'll pop on a lid. This should keep things just a little safer in case it spins real fast. We'll secure everything in place like so, and fit a minor gear reduction for future LEGO builds. This will make it more useful in case we want to power something like a massive LEGO vehicle. I'm expecting this motor both to spin fast and have excellent torque. So back to 12 volts and our 3.2 amp limit.
Hi, let's give her a bit of juice.
Wow, it certainly responds well.
Let's see what the torque is like with a 3-to-1 gearing.
You can see here that the current draw increases when I try and hold the output.
Wow.
Though of course, there's no chance I can hold on to it.
Whoa.
What a lovely sound.
No chance. We're maxing out at 23 watts. What's the torque like on the rotor itself? We'll just do low speed here. Wow, that is torquey. Very impressive. And what speed are we getting? Just under 10,000 RPM.
So now we have good speed and good torque. But what if we can get even gooder torque? Here I've got another rotor that can fit much bigger magnets. Now these guys are 15 by 5mm N52 magnets. It's obvious even just fitting these in place that they're so much stronger.
Oh, well, the last one's always the hardest. It's not so bad. And I'm also hoping that because these are a lot bigger than those, they should have a lot more torque. These feel so much more powerful.
Again, we'll pop on our lid, and in she goes.
That holds in place really well. I've lubed up the little holes here as well. Well, that spins beautifully.
12 volts, 3.2 amps as usual.
Let's see what sort of speed we get now. Oh, that is so smooth. Wow!
This one just sounds so beautiful. I love the hum it makes.
Getting about 4,000 RPM. Okay, we're maxed out. Yeah, about 6,500 RPM. I love the noise this thing makes.
Now there's fewer magnets, so you'd think it'd run faster, but the magnets are much bigger, creating much more drag against the metal cores. So it's slightly lower RPM, but I'm willing to bet the torque is far better.
Wow.
And what's the torque like straight out of the motor?
Okay, this is about 2/3 the way up on the speed controller. 33 amps. 3 amps. Uh-oh. Not surprising, with all this torque and vibration, these nuts are coming undone.
Huh, it actually looks like it might have friction melted some of the plastic a little. Well, let's see how this beauty performs in the wind thrust test.
Alright, let's see what she's cooking with. Yeah, it's flowing nicely.
By the way, if you like experiments like these with Lego and technology, feel free to subscribe or drop a like. Cheers!
Okay, we're maxed out. We're getting 20 watt draw, 30 grams of thrust. Feels lovely. Now, it's not surprising it's maxing out here. This is more of a torque monster than a speed monster. What that does mean though is that this is a teeny tiny blade, but we could probably put a much bigger prop on here. At least we know at this rate 1.6 amps is very sustainable. Yeah, this propeller is just way too small for this monster.
So out of interest, let me print an even bigger prop. I'd imagine even this bigger one won't pose a problem for this motor. Wow, maxed out it's drawing an extra 5 watts of power, which I think indicates it's faring pretty well with an increased load. But for now, what if we go even bigger? These massive blades have an angled axle hole so we can attach it to some Lego wheels and have around a 16-degree pitch on the blades.
Oh, I have no idea if this is going to be able to hold on to it. This doesn't seem like one of my smarter ideas, so glasses on. Oh, I hope these things don't snap off. Here we go.
Now this is where we find out if 2mm is thick enough and strong enough to hold on.
Whoa! I don't like this. God. That is wild. That is very windy.
And indeed, with these massive blades providing more resistance, we're maxing out at 3.2 amps at only 11 volts. I'd love to chuck some more power through it, but I just don't think the coils would manage it for any more than some short bursts. Pretty damn impressive for a motor made of Lego though. And if you'd like to see some behind the scenes of how I make these things, feel free to check out my Patreon, link below. It does make me wonder though if it's actually possible to fly a Lego built aircraft. Sounds insane, I know, but maybe not too insane? Okay, the next important question is just how much weight these motors can lift, which should indicate their torque. Let's start with our standard Lego XL motor as a comparison, seeing if it can lift around half a kilo. The bottle is attached to the spool here, and it looks like this is far too easy for it.
Okay, what about 2.5 kilos? This one I'm not so sure about.
Very impressive considering it's only blowing about 6 watts.
Ooh.
Okay, what about 3.5 kilos?
Yeah, I have a feeling something's gonna break here.
Wow, this is very impressive.
Wow.
But it pretty much stalls right here.
Close to stalling. Yeah, that's about it. Well, that's quite impressive. It actually broke the axle.
So with all this internal gearing, the speed is slow at around 220 RPM, but torque is excellent, stalling at almost bang on 3.5 kilos. Now, let's try my brushless motors. Starting with our teeniest one, which I'm adding a bearing to give it a helping hand and reduce friction. This one has 3 metal core coils.
Oh yeah, this spins way smoother. Oh, these wires are so thin, there's no way these will take 3.2 amps. Out of interest, let's see what wattage this thing draws when it's near to stalling.
I think those squeaks is the bearing slipping a bit.
Ugh.
Yeah, we'll try that again. During those squeaks, it looks like we're drawing a peak of about 4.8 watts. Now I'm going to limit this to about half an amp, otherwise the coils might overheat a bit much. As we spin her up for a speed test, we're drawing about 4.5 watts, and we're getting a somewhat respectable 7,500 RPM. But how is its torque? Let's see if it can lift this empty bottle. Ugh, sorry about that nasty noise.
One more try.
Nope, what a useless motor.
Nope. Can't even lift 24 grams.
It's honestly just a bad design on my part. But what about our speed demon here? It's coreless and runs crazy fast, but does it have any torque? Let's try half a kilo here.
Ah, okay. Got a bit of lift, but then dropped it. Let's try that one more time. Whoop. We'll pour just a little bit of water out. Not quite.
Okay, just a little less water.
Well, yup, that worked. We're getting somewhere just north of 350 grams.
Now let's try our axial flux motor with magnetic cores. And we'll see if it can lift 2.5 kilos. This does feel like a lot though.
Okay, let's see. Not quite.
Okay, let's drop down to 2 kilos.
Let's try that one more time. Not quite 2 kilos. What about 1.5 kilos?
Yeah, cautiously optimistic here.
Oh, it's just stalling. So almost bang on 1.5 kilos.
And then finally our radial flux brushless motor. I assume this water bottle test will be easy.
Yep.
Okay, a bigger water bottle. Also easy.
Oops. Just got a bit caught.
Both bottles.
Whoop. Yup.
I'm going to stick on this longer metal axle. And upping to 2.5 kilos.
Yeah, not quite. We'll try that one more time. Yep. Can't do 2.5 kilos.
Now back down to 2 kilos.
Whoop, yup. Easy. So somewhere between 2 and 2.5 kilos.
Pretty damn good for a Lego motor that can also spin up to over 6,500 RPM at only 12 volts. Now, before we do a final speed test on our little guy, let's do a quick recap of how these motors compare. At 9 volts, our Lego XL motor is at top speed of 225 RPM, a peak draw of 13.5 watts near stalling, a wind thrust of who knows because it was way too slow to bother to measure, and it can lift an impressive 3.5 kilos. Our tiny motor at 12 volts has a top speed of 7600 RPM, a peak draw of 4.8 watts, a wind thrust of nothing because I couldn't get it to drive a prop, and it can lift bugger all. Then our little speed demon here at 12 volts has a top speed of, well, we'll figure that out shortly, a peak draw of 38 watts, a wind thrust of 57 grams at 38 watts, and it can lift just over 360 grams. Our axial flux magnetic core motor then has a top speed of 3400 RPM, a peak draw of 38 watts, a wind thrust of 30 grams at 25 watts, and can lift just over 1.5 kilos. Finally then, our radial flux magnetic core motor has a top speed of 9800 with the smaller magnets, or 6700 RPM with the bigger guys. A peak draw once again of 38 watts, a wind thrust of 30 grams at 20 watts, which is 5 watts less than the axial flux motor, and can lift just over 2 kilos. Now out of all of these motors, the one I'm actually having the most fun with is this small speed demon. It fits easily into even small Lego contraptions like this wind-powered car. This thing barely needs any juice to get up to a pretty decent speed. And it makes me wonder if I should maybe make a hovercraft with this thing. Okay, now that everything is lubed up, let's give this another speed test to see if we can max it out.
Still runs smooth.
I'm going to use this printed marker wheel to reduce any potential speed wobbles. Oh man, I really love the sound of this thing. Okay, let's see what we're cooking with. The thing I'm really impressed by is how little this thing is drawing at even 30,000 RPM. Now this horrible noise here I think is the speed controller just wanting higher voltages.
43!
But we're easily hitting 44,000 RPM while drawing only around 5-ish watts. I'm incredibly impressed. I'll admit, my heart was racing a bit measuring this.
Crazy.
But I'm incredibly happy with how this thing performs. So for their size, I reckon these two are probably our most useful homemade Lego brushless motors for future builds. Cheers for watching, folks!